Thank you for stopping by. Hello, my name is Irfan. I'm a maker. This is video number 3 in a multi-series set of videos where I capture my journey designing and making an oud instrument. If you have not viewed my video number 2, it may be helpful. In that video, I've captured the anatomy of the oud instrument and provided some foundational information on the instrument and the different parts. I've provided a link to video number 2 in the description. In this video, I'm going to talk about how the oud instrument produces sound, in particular, the role that the bowl of the instrument plays in that sound production, why it exists, what it does, and some of the guiding principles that shape its design. Today's video is not about mathematical equations or advanced acoustics. I've planned them for future videos possibly. This video is just the foundation, okay? Some of the concepts and ideas that I'm going to present are a little deeper, and I will visit them over the course of the series. But this is just the foundation, understanding what matters most, not mastering everything at once, okay? Okay, so let's see how sound is actually produced on the oud. I'm going to strike some open strings on my oud. Please pay close attention to the strings, and I'm going to explain how the sound is actually produced, okay? So I'm going to strike a string on my oud. I want you to observe what happens to the string. My oud is tuned do to do. So this is low do, low C. I hope it's visible on the camera. The string vibrates. Okay, so when I attack the string with my risha or my thumb, I'm putting energy into the system, okay? The first law of energy conservation, I think I may have mentioned it in one of my earlier videos. Energy can never be created nor destroyed, it can only be transformed, okay? So this vibration of the strings, right, this is mechanical energy, okay? And the energy and this mechanical energy moves through a chain, okay? So string, bridge, soundboard, air, bowl, sound hole or sound holes, and the listener's eardrums, okay? So string, bridge, the soundboard, air, the bowl, the sound holes, the listener's eardrums, okay? Okay, so when I strike the string, right, it starts to oscillate at a specific frequency. This is my low do. So this frequency is 65 Hertz. So starting from the rest position, it will extend to one extreme, comes back to rest, extends to the other extreme, comes back to rest. So this completes one oscillation or one cycle, okay? So this low do string, right, it will oscillate or vibrate at 65 Hertz or 65 cycles per second. And each one of these strings have a different frequency. Open strings have a different frequency. So, for example, my Re is 146. Sol is 196, and so on and so forth, okay? Now, another concept pertaining to the frequency is I can change the frequency, right? So all I do is I just change the length of the string, okay? So I can change the frequency. Frequency is inversely related to the length of the string, okay? So if I play open string, right, So that length of string is from the nut to the bridge. If I put my index finger, right, so that's Mi half bemol, 160 hertz. So I went from 140, actually 146.7, 146.8, so close to 147 Re to Mi half bemol, which is 160 Fa, 175, right? So I'm increasing by reducing the length of the string. I'm increasing the frequency. There's an inverse relationship, and like I said, in this video I do not want to get into the mathematics, right? In future videos I will, but this is another important concept. So another way to say it is that I just shifted the starting point of my string vibration. Okay? So instead of the string starting the vibration from the nut, it's starting the vibration from where my index finger is on Mi half bemol. Okay? Okay, so let's continue to follow this energy path, right? So the string oscillates more or less parallel to the soundboard, okay? But mathematically it's a little more complex, but these oscillations are not perpendicular to the soundboard, okay? So think about from resting position, pulling a string that is tied on both ends, right? So pulls up to the widest point of the oscillation, goes back to the rest position, and then pulls to the other direction, okay? So that's the general movement of these string oscillations, right? Now the string, right, it is directly tied to the bridge, okay? So as the string continues to oscillate back and forth, okay, this bridge is acting as a pivot point, so a kind of a lever, right, and starts to rock back and forth. Mathematically, it's a little more complex than this, right, but for this conversation, the bridge rocks back and forth as the strings oscillate more or less parallel to the soundboard. So this back and forth rocking motion of the bridge creates a twisting force, okay? So the twisting force on the bridge, right, it causes the soundboard area that is directly in front of the bridge to be pulled slightly upwards, and the soundboard area that is directly behind the bridge to be pushed slightly downwards, and vice versa. It just depends on the movement phase, okay? So this particular concept, it is called top rotation or belly bulge in acoustic instruments, and is key in the energy transfer path, okay? Okay, so let's continue to see what happens next, all right? Notice where the bridge sits, right? This bridge placement is not random, all right? The bridge is glued to the soundboard at the widest portion of the soundboard, okay? So to illustrate the movement of the soundboard, right, imagine a seesaw, right? In a seesaw, the pivot point moves very little, but the ends move a lot, okay? In an oud, the soundboard is very thin and flexible, okay? It's very thin and flexible. So this is, 1.5 to 2 mil, so it's extremely thin and it's extremely flexible. So this flex under the bridge, right, that I just explained, right, is not just contained in the area under the bridge, right? This flex, this energy, right, is pumped into the entire plate of the soundboard. Okay, so now the soundboard is forced to vibrate at the same frequency, including harmonics, as the strings. Okay? All right, so now we're getting somewhere. Okay, so the soundboard starts vibrating. What's on each side of the soundboard surface, right? Okay, it's air, right? So this is the outside surface, air. On the other surface of the soundboard is air, okay? So when the soundboard starts vibrating, it transfers its energy to the surrounding air, okay? It causes the air molecules to compress and decompress in a cyclical pattern, all right? Both inside and outside the bowl. So when the soundboard moves outward, right? Because it's moving at the same frequency, or it's oscillating at the same frequency as the frequency of the string, right? So when it starts those oscillations, right, it transfers that energy to these air molecules, right? So when the soundboard moves outward, so similar when I showed you on the string, right? Right, so this is one cycle, rest, up, rest, down, rest, okay? Soundboard, this is the resting position of the soundboard. So it's similar to the strings, oscillation it's more complex than that. I'm not going into modes and the complex mathematics between how the soundboard actually moves, but in very simple terms, right? When the soundboard moves outwards, the outside air molecules, they compress, right? The molecules don't go too far, right? The air molecules don't go too far. They compress, and inside the bowl, air molecules, they decompress, right? And vice versa. So it continues in that cyclical compression and decompression pattern of the surrounding air molecules, okay? So what that does, it creates these longitudinal pressure waves that travel outward from the vibrating source. This is my vibrating source, right? And the compression and the decompression of the air molecules is happening right around this vibrating source. So those longitudinal pressure waves, they travel outward of this vibrating source, right? And these cyclical back and forth pressure changes, they carry the sound energy to our ears, okay? Where the eardrums start vibrating in response. And that is how we hear sound, okay? So to recap what we reviewed in terms of the energy path, right? So when I strike the string, it starts oscillating at a certain frequency. The mechanical energy is transferred to the bridge, which starts rocking back and forth. The bridge is glued to the soundboard, right? So the area right in front and right behind the bridge on the soundboard, that starts to flex slightly outward and inward depending on the movement phase, okay? The soundboard is extremely flexible, thin, so that energy gets transferred to the entire plate of the soundboard, okay? Right? So as the soundboard starts oscillating at the same frequency as the strings, it compresses and decompresses the air, right? So inside the bowl, right? And outside the surface of the soundboard, and which in turn generates these longitudinal pressure waves that travel outward of the vibrating source, get to our eardrums, and in response, our eardrums start vibrating at the same frequency as the frequency of the string or strings, okay? And it includes harmonics. You know, each one of these vibrations include harmonics, okay? So now let's ask a question, right? So what if there was no bowl, right? because in the path that I just described, right, I've not touched on a lot because I'm trying to keep this as simple as I possibly can. So I have not touched on Helmholtz resonator. I have not touched on, because the soundboard movement, the pattern is not that simple, right? It is a very complex pattern that the soundboard takes in terms of, the oscillations, okay? So I haven't touched on the modes, and there's several other things I haven't really touched on in any level of depth or detail, okay? But let's ask a question. So what role does the bowl play? What if I remove the bowl? What happens? Will I still get sound? Okay, so let's take a look at that and let's explore that a bit. So even without the bowl, right, we have air on either surface of the soundboard, okay? So the energy path, string, bridge, soundboard, air, compression, decompression, the longitudinal pressure waves, right? That's still intact, right? Even without the bowl, okay? So yes, I mean, without the bowl, we will still get sound, right? But it would be very quiet, okay? There will be no resonance, and the sound will be extremely thin, okay? So the oud bowl, right? So this bowl, okay? Right, the primary function, there's actually two primary functions of the bowl, okay? The first function that the bowl serves is that it amplifies the sound, okay? The second function it serves is that it shapes the sound, so there is tone shaping that takes place. Now so if you look at this bowl, right, it's a pear-shaped bowl, and that's not by accident, right? If you change that shape to a square shape, are you going to get the same characteristic, the deep and mellow tone of the oud? No, right? So that shape is not by accident, okay? So again, the two key functions that the bowl serves, first one is it amplifies the sound, and second is it shapes the tonal characteristics of that sound, okay? And in addition, right, the design of the bowl also provides the structure, right, to anchor the bridge, the strings, and the neck, because in my previous video, I had mentioned that the neck is attached to the bowl using either a dowel or a dovetail joint, right? The bridge, right, it's glued to the soundboard, and the soundboard is glued to the bowl. So the bowl also serves as a key structural component of the instrument, okay? I think this is a good point to ramp off video number 3 in order for me to explain how the oud bowl in combination with the soundboard produces the amplified sound and the oud's unique tonal characteristics. Yeah, you got to get into some acoustic engineering, some mathematics and technical concepts, which I for sure plan to capture in future videos, but that's not going to be video number 4. This is where tradition meets engineering. Tradition and craftsmanship passed over generations or thousands of years, from father to son to daughter, from teacher to student, from mother to son to daughter. Tradition tells you what already works. Engineering will tell you where the boundaries are and what will possibly not work. In my next video, video number 4, I'll be presenting the approach I took to design the oud bowl and also some of the available options. In addition, I will share the process I followed to design and construct the oud bowl profile template, the rib profile template, as well as the neck and the tail block. And also I'm going to share the mistakes I made and what I learned from those mistakes. Hopefully you can avoid those and come up with a better approach. And finally, I'm going to share some of the tools that I used and some tools that I made along the way. Thank you for stopping by. I hope you will follow along my journey with me. I hope to see you in video number 4.